What specific problem does Opt-CWM aim to solve in the context of self-supervised optical flow estimation, and how does it compare to existing methods?
Opt-CWM aims to solve the problem of suboptimal motion extraction in self-supervised optical flow estimation caused by hand-designed perturbations that are often out of domain and not context-specific. Existing methods, such as CWM, rely on fixed perturbations that can lead to inaccuracies in real-world scenarios, particularly when perturbations do not move with the objects they are meant to track. In contrast, Opt-CWM introduces a learnable neural network to generate context-specific perturbations, allowing for more accurate flow predictions by adapting to the local appearance of target points. Additionally, Opt-CWM employs a joint optimization strategy that connects flow predictions to a next-frame predictor, enhancing the robustness of the flow extraction process. This approach enables Opt-CWM to outperform state-of-the-art self-supervised motion estimation methods and even some supervised methods in challenging real-world benchmarks, demonstrating its effectiveness in addressing the limitations of previous techniques.
How does the proposed method, Opt-CWM, work? Illustrate the steps involved in the counterfactual world modeling process and how it processes video frames through perturbations.
The proposed method, Opt-CWM, operates through a process called Counterfactual World Modeling, CWM, which involves several key steps. First, it utilizes an RGB conditioned next frame predictor, denoted as $text RGB, which is trained with a highly asymmetric masking policy to predict the next frame based on a visible first frame and a partially visible second frame. To extract motion properties, a counterfactual perturbation is applied to a specific pixel in the first frame, creating a modified input image. The model then predicts the next frame for both the original and perturbed images, and the flow is computed by analyzing the difference in predicted pixel locations between these two conditions. Finally, the perturbation generator is optimized through a joint training process with a flow-conditioned, next-frame predictor, ensuring that the perturbations are context-specific and improve the accuracy of flow vector estimations. This end-to-end optimization allows Opt-CWM to effectively learn and adapt perturbations for real-world video scenarios, outperforming existing methods.
Can you come up with a simple yet illustrative example of how the counterfactual perturbation generator operates? Walk through the main algorithm steps with a specific example of tracking a point across frames.
The counterfactual perturbation generator operates by creating a context-specific perturbation to track a point across frames. For instance, consider tracking a pixel located at p_1 equals row_1 col_1 in the first frame, i_1. The algorithm begins by perturbing the image at this pixel location by adding a colored Gaussian patch, delta, to create a counterfactual image, i_1 equals i_1 plus delta. Next, the RGB condition next frame predictor, $text RGB generates predictions for both the perturbed frame, i_1 foot, and the original frame, i_1, resulting in _2 and _2 respectively. The difference image, $delta, equals i_2 is then computed, and the predicted location of the point in the next frame, p_2, is determined by finding the peak in this difference image, effectively tracking the motion of the point across frames. This process allows the model to adaptively generate perturbations that are tailored to the local context of the image, enhancing the accuracy of motion estimation.
What are the theoretical or practical advantages of utilizing Opt-CWM compared to traditional supervised methods and existing self-supervised approaches in terms of motion estimation accuracy and efficiency?
Opt-CWM offers significant theoretical and practical advantages over traditional supervised methods and existing self-supervised approaches in motion estimation. Firstly, it eliminates the reliance on synthetic data and hand-designed heuristics, which are common limitations in supervised methods, allowing it to be trained on unlimited in-the-wild videos, thus enhancing generalizability. Secondly, Opt-CWM employs a learnable counterfactual perturbation generator that adapts to local image contexts, resulting in more accurate motion estimations compared to fixed perturbations used in traditional methods. Additionally, the joint optimization of flow predictions with a flow-conditioned next-frame predictor ensures that the flow outputs are tightly coupled with the reconstruction loss, leading to improved accuracy. Empirically, Opt-CWM has been shown to outperform state-of-the-art self-supervised motion estimation methods and even some supervised methods in complex scenarios, demonstrating its efficiency and robustness in real-world applications.
How has the effectiveness of Opt-CWM been validated? Describe the datasets used for testing, the metrics for evaluation, and any ablation studies conducted to support the claims made in the paper.
The effectiveness of Opt-CWM has been validated through extensive testing on several datasets, including TAPVID, Davis, and Kinetics, with TAPVID serving as the primary benchmark for evaluating motion estimation accuracy in real-world video scenarios. The evaluation metrics employed include average Jaccard (AJ), average distance (AD), occlusion accuracy (OA), and occlusion F1 of 1, which collectively assess point tracking and occlusion prediction performance. Additionally, ablation studies were conducted to compare Opt-CWM against various hard-coded perturbation methods, demonstrating that learned perturbations significantly enhance performance. The results indicate that optimizing counterfactual perturbations is crucial for achieving superior flow predictions, as evidenced by the substantial performance gains over prior CWM works. Furthermore, the paper highlights that models with larger input resolutions and those utilizing multi-mask inference and multi-scale refinement procedures also show improved results, reinforcing the robustness of the Opt-CWM approach.
What limitations or potential drawbacks does Opt-CWM have, especially regarding its implementation in real-world scenarios or under certain conditions?
Opt-CWM has notable limitations, particularly concerning its reliance on a learnable perturbation generator, which, while designed to be context-specific, may still produce suboptimal perturbations if the training data does not adequately represent real-world scenarios. The perturbations generated can be out of domain, leading to inaccuracies in motion extraction when applied to complex scenes where the visual context significantly varies. Additionally, while Opt-CWM outperforms state-of-the-art methods, its performance may still falter in situations where the underlying assumptions of the model do not hold, such as in highly dynamic environments with unpredictable motion patterns. Furthermore, the model's dependency on the quality of the RGB condition next frame predictor means that any deficiencies in this component could directly impact the accuracy of flow and occlusion estimates. Lastly, the need for extensive computational resources for training and inference may limit its practical deployment in real-time applications.